Alright, we are ready to apply our differential relationships between load, shear, and moment on a beam. Right, we've got a beam here that is 18 feet long, and it is subjected to a snow load, as a snow drift that just so happens to be 0 at one end and peaks out at the other end. Now this usually happens because this beam is right up next to some sort of wall where the snow can pile up like this, and it's not always the case that the base of this triangular load would be all the way out here to where the end of the beam is at. It's a little bit academic to do it that way, but I wanted to do it that way. All right? So we've got a peak intensity out here that is 300 pounds per foot. That's the intensity, and 0 out here at the far left. Okay, we're going to find the equations for the internal shear and bending moment as a function of position along the length of the beam, and we're going to do so using integration approaches. Right, so we're going to establish our coordinate system at the left. Right, that x is equal to 0. We don't have to do it that way, but I'm going to declare that I'm going to. And then let's identify the coordinate system and the force boundary conditions. Well, we just did the coordinate system. The force boundary conditions, we go back to the relevant equation is that the second derivative of the moment is equal to the load. That comes from the differential relationship between the load and the shear, dv dx equals w, and the differential relationship between the moment and shear, that dm dx equals v. So the rate of change of the shear equals the load, and the rate of change of the moment equals the shear. That's the second order differential equation, and we've got two boundary conditions that are associated with that. Well, here we've got a pin support, no applied moment, so what that tells me is that at x equal to 0, the moment, the internal moment, not some global moment of a force times it, no. The internal bending moment is equal to 0 at that location. At x equal to L, which is 18 feet, then the moment is also equal to 0. We have a roller support. That support can't provide any resistance to rotation. There's no moment to be applied there to prevent any rotation. Right? So those are our two and only two boundary conditions that we have. Yes, I could go find out some reactions here, and we will maybe eventually do that, but not right now, because those are not boundary conditions. The boundary conditions are what's the natural state that's happening without any calculation. And so in this case, that would be the two that we've identified right there. Right? So we're going to do this as one step at a time. If we're going to do integration, we got to get functions, and the intensity of the load varies, all right, as a function of position. And so we got to be real careful how we go about getting this. And when I say real careful, well, what's our sign convention? Remember that we're using upwards in this expression as positive. So all of this load is really negative, right? And so we have something that for the load is a y equals mx plus b kind of expression. Well, the intercept is 0, right? At x equal to 0, w is equal to 0. So there's no intercept. There's just the slope that's there. Well, okay, we've got 300 pounds per foot out at the far right, and that increases linearly at the rate of 300 divided by 18, and it's all downwards. So the load intensity function is what you see here, and that 300 divided by 18 is 16.67, so minus 16.67, and that would be pounds per square foot times x. And p is a little weird. Let's make that lb, pounds per square foot along the length. Right, that's the intensity of the distributed load, not the load, but the intensity of the distributed load as a function of x. Right, now we have a calculus problem. So, right, we can go find the shear function, because the shear is the integral of dv, and dv is equal to w times dx. But we just cleverly found out what w was, and that's a function of x. That's minus 16.67 times x, and then of course times dx. So we integrate that, and that will be minus 16.67 divided by 2, or minus 8.833. Of course the 3 is repeating. X squared, and that's what most of your calculators will say, and they are wrong. We're missing something. That constant of integration. Oh, yeah, everybody knows. No, you gotta get it. And we're gonna have more than one. If we don't get it, we're gonna be just nothing but wrong. So we've got to have it there. And not only that, but so let's now solve for that constant, but no boundary condition involves C1. So we can't do anything. We have to go to the next stage. Alright, so what's the next stage? Well, go find the moment. The moment equals the integral of dm, which dm is equal to v times dx. And so now, hey, we just found v though. Isn't that kind of cool? So minus 8.33 x squared plus c1. See, we've got to have it in there. All that times dx, because now we'll have minus 8.33 x cubed divided by 3 plus c1 times x plus another constant of integration. This is why your calculators almost get this wrong every single time, because they won't give you the constant of integration. And you have to have them. Because now we got to go solve for these things, right? And we know that one of the conditions is that x equal to 0, m at 0 is equal to, well, minus 8.33 over 3 times 0 squared plus c1 times 0 plus c2, and then, oh, well, the whole thing, that boundary condition was that the moment was 0. So therefore, we just found out c2 equals 0. All that work just to find out it was 0. But yeah, that's right. It won't always be 0. And then, when would it not be 0? Well, when m is not equal to 0 at x equal to 18, then c2 wouldn't be that value, would it? Well, when would that not be 0? When I put applied couple out there, that's when it wouldn't. Or here, or, well, rather at the left, that's in other words. Alright, so m of 18 is going to be equal to minus 8.33 times 18 squared divided by 3 plus, I'm presuming I've been very careful about units here, and that turns out at 18 feet to also be equal to 0, so therefore c1 is going to be equal to, well, that's going to be equal to 50. How about that? A nice little number. What are the units on 50? Well, note what's going to happen. C1 showed up in the shear. That's kind of interesting. So let's go back. Our shear expression just became then minus 8.33 x. I feel like I did something wrong. In fact, I know I did something wrong. Because I had x squared here, and I put x cubed down here, but then I didn't translate it through properly. Right there. Bummer. So actually, C1's not 50, it's 900. Now, I would have found that mistake in the next stage here, because notice what's going to happen. Shear at 0 would have equaled by the function 900. Well, now let's go find the reaction in our system. Right? We can sum moments about, let's call that point B, that point A. Let's sum moments about point B, because then we'll have AY times 18 feet minus 1/2 of 300 pounds per foot times 18 feet times a moment arm, which is going to be 1/3 of 18, that's 6 feet, and that has to be equal to 0. Right now, mathematically, the 18s cancel out. 300 divided by 2 is 150, and 150 times 6 is, wow, 900 pounds. So note the free body diagram that would happen right there at the left, that we'd have the 900-pound reaction going up, we'd have 0 distributed force and a positive V acting downwards on that right-hand exposed face. So V at 0 would indeed equal 900, and that's exactly what showed up right there. That's pretty cool. The shear was actually equal to the reaction right there. Right? And then do the same thing over here at B, V at 18, and that would be 18 times 8.333, whoops, 18 squared times 8.333333 plus 900, and it would equal 3600. I don't know if I like that number. I feel like I maybe made a mistake here, because 3600, that would be 1/4 of the load. I don't like that. Something's not right there. What's our total load here? 300 times 0.5 times 18 is 2700, and so this should have been 8. That 3600 should have been times 18 squared. Oh, because I never added the 900. That's the mistake I made. Hello. But notice what I was doing to check all that. And that was, hey, you know, bam, this stuff, the reaction, you're going to find out that was 1800. And note when you do the free body diagram over here, you're going to have a reaction up of 1800. The positive will be showing upwards, but of course that's a negative value that we just found. Sorry. And so minus 1800 goes the other way, sum of forces in the y, bam, that's going to also work out right. This little distributed load goes away right as we get right to the end, infinitesimally close to the end on that. So, wow, the shear in the ends actually are right there associated with the reactions. Won't always be the case, because if there's an overhang and load out in the overhang, that will change things a little bit. Right? So what's our answer here? Well, one of our answers is that the shear varies in a parabolic fashion. The load was linear, we integrate, we get a parabola. The moment varies in a cubic fashion, right? And I guess I never really wrote out the equation, so let's do that. M of x equals minus 8.333 repeating over 3x cubed plus our C1 value, that's 900x. C2 is 0, and so there's your worked out with numbers 1 here, right? That's a cubic function because we integrated shear, and it was parabolic, and shear was parabolic because the load was linear.